Now let's talk about the common ion effect with respect to sparingly soluble salts. You may remember that we talked about the common ion effect last time when we were talking about buffers. Well, now we're going to talk about it with respect to the solubility of insoluble, or what we call sparingly soluble salts. So for our purposes, we're going to select a sparingly soluble salt, which is silver chloride. It has a Ksp of 1.8 times 10 to the minus 10, means it's not very soluble in water with such a small Ksp, or equilibrium constant. It's very reactant favored, means it favors the solid form. So we're going to do an experiment. First of all, we're going to throw silver chloride mathematically into pure water, and we're going to calculate the molar solubility. Then we're going to take our silver chloride, the same silver chloride, and we're going to throw it into a solution that has the common ion, chloride ion, by virtue of dropping it into a hydrochloric acid solution. So first of all, let's put our silver chloride in water. So we have some mass of silver chloride that we drop in water. We don't have any silver ion to start with, and we don't have any chloride ion to start with. The change will be minus X for the silver chloride. That means we're going to lose a little bit of mass. And for every 1 mole of silver chloride that dissociates, we get a mole of silver ion, which will be plus X for silver ion and plus X for chloride. We go ahead, we have less mass at the equilibrium point, and we'll go ahead and see how much silver ion and how much chloride ion we have. In order to solve this for the molar solubility, we write our Ksp expression, and our Ksp expression is equal to the concentration of silver ion plus times the concentration of chloride ion. And then we're going to go just plug in our values. The Ksp for silver chloride is 1.8 times 10 to the minus 10. Now, that's 10. The concentration of silver ion is X. The concentration of chloride ion is X. X times X is simply X squared. And so now we need to solve for the molar solubility, which is just X, and we're going to do that by taking the square root of both sides of the equation. And when we do that, we get 1.34 times 10 to the minus 5 molar for our molar solubility. So that tells us how many moles of silver ion and how many moles of chloride ion are in solution when we drop silver chloride in pure water. Now what we're going to do is we're going to drop the silver chloride into a 1 molar concentration of HCl. And you remember HCl is a strong electrolyte. You put it in water, it completely ionizes into hydrogen ion and chloride ion. So we'll have a 1 molar concentration of hydrogen ion, a 1 molar concentration of chloride ion. Well, since hydrogen ion is not common it's not a common ion for silver chloride, it actually doesn't make any difference, or not a substantial difference, in the solubility of silver chloride. So we'll drop that same mass of silver chloride into our hydrochloric acid solution. We don't have any silver ion initially, but we have a 1.00 molar concentration of our chloride ion initially. Now, our change is again going to be minus X. Our change here will be plus X, and our change here will be plus X. We add everything up, we'll have less mass of silver chloride at the equilibrium point. We'll have X moles of silver ions and 1.00 plus X moles of chloride ion. Well, the X value is going to be incredibly small, particularly with a Ksp of 10 to the minus 10, so we can very confidently ignore the X value with respect to the 1 molar. We go ahead and we set up our Ksp expression again. Ksp is equal to the silver ion concentration times the chloride ion concentration, And we put our values in. X is the silver ion concentration, and then 1.00 molar. We have a huge amount of chloride ion, our common ion for silver chloride, already in solution. We've got a Ksp of 1.8 times 10 to the minus 10. We solve the problem simply by dividing both sides by 1.00. Well, that cancels over here, and then 1.8 times 10 to the minus 10 divided by 1 molar is simply an X value that equals to 1.8 times 10 to the minus 10. Now, we can see how much our molar solubility has dropped due to the presence of the common ion. And this is due to Le Chatelier's effect, or Le Chatelier's principle. Since we have provided so much product in the form of the common ion chloride ion, the reaction shifts hugely over here toward the reactant side, and our molar solubility drops tremendously. This is going to cause the silver ion concentration to go way down on the order of 100,000 times. So our molar solubility is considerably less when we have a common ion present in solution. Now I'd like to perform an experiment mathematically to determine whether or not we can form the precipitate lead 2 chloride from its component ions in solution. And those component ions are going to come from different substances that I put into water. So I have a 1 liter, let's just start out with 1 liter of water. I'm going to take 0.010 moles of lead 2 nitrate and 0.010 moles of hydrochloric acid, and I'm going to put both of those compounds into this 1 liter container. So if you remember, all nitrates are soluble, so the lead 2 nitrate will completely dissociate into lead 2 plus ion and to 2 nitrate ions. Now the nitrate ions are not part of lead 2 chloride, and so they're not common, and so we can ignore them. They're just going to be spectator ions in this reaction. But the lead 2 ions that we put in solution, those guys are part of lead 2 chloride. So they'll float around in solution 0.01 molar. And then we put in some hydrochloric acid. And we put hydrochloric acid, a soluble strong electrolyte. It completely ionizes to H plus and chloride ion. The H plus, once again, is not part of our lead 2 chloride compound, and so what we do care about is the chloride ion we put in solution. So now we've got 0.01 molar solution of chloride ion, a 0.010 molar solution of lead 2 ion, and we want to know whether a precipitate forms. Here's how we're going to make the determination as to whether a precipitate forms. Just to remind you of this little diagram I like to use. So if we had started out with lead 2 chloride, the lead 2 chloride would begin to dissociate, and initially Q would be less than K, and it would dissociate until Q was equal to K, and at that point the forward reaction of dissociation would equal the reverse reaction of a precipitate forming. But in our experiment, we're starting out with concentrations of our products. And remember, you can get to equilibrium from either the reactant side or the product side. You learned that in chapter 15. So we're starting out with Q being greater than K because we're all products. So the reaction is going to run in reverse. Now the question is whether a precipitate will form. The precipitate will form when Q is equal to K. That's the point, the low energy point, when we have so many products that are in solution that the equilibrium won't sustain free ions in solution, and so it forms the lead 2 chloride to remove some of those ions from solution. So all we have to do is calculate the current state of the reaction, the Qsp, compare it to the Ksp. If Qsp is greater than K, a precipitate forms. If Qsp is less than K, no precipitate will form. You need more product in solution until that occurs. So all we need to do to determine whether a precipitate will form is look at the reaction. You always start with the reaction. This is lead 2 chloride in equilibrium with Pb 2 plus in aqueous solution plus chloride ion, and there's 2 chloride ions, and they are in aqueous solution. Now we know that we have 0.010 molar concentration of lead 2 chloride, and we also have a 0.010 concentration of our chloride ion. We'll go ahead and we'll assemble our Ksp expression, and our Ksp expression is just going to be the concentration of lead 2 plus times the concentration of chloride ion squared. So we go ahead, plug those concentrations in, 0.010 raised to the first power and 0.010 squared because of the squared term. And then we go ahead and we calculate our Ksp. And if I do the math on this, this is just 0.010 times 0.010 squared, which is 0.010 cubed. That gives us a Ksp that's equal to 1 times 10 to the minus 6. If I look at my Ksp versus my Ksp is 1.6 times 10 to the minus 5. My Ksp is 1 times 10 to the minus 6, and I can see that my Ksp is less than my Ksp. That puts me over here on this side of my little diagram. And if I'm over here on this side, that means that that the reaction will continue to run forward to form more product. Well, I don't have more product. What it really means in this particular instance is that no precipitate forms, because a precipitate won't form until the Q is at least equal to the Ksp. That's when you get precipitate formation. So the bottom line here is, if you're given concentrations of ions that will form a compound, as long as Q is less than K, no precipitate forms, but when Q is greater than K, you get a precipitate forming.